Let's dive right in. Welcome to today's Explainer. If you're a focused learner looking to truly master the foundational building blocks of organic chemistry, you are in exactly the right place. Today, we're going through a structured, highly energetic masterclass on aldehydes, ketones, and carboxylic acids. Now, these compounds aren't just abstract textbook concepts. They are literally the essential constituents of the fabrics we wear, the flavorings in our food, everyday plastics, and even life-saving drugs. So, let's get ready to decode the molecules that shape our world.
Here is our roadmap for today. We'll be covering 1. Meet the carbonyl group. 2. Naming rules. 3. Physical properties. 4. Key preparation methods. 5. Crucial chemical reactions. And 6. The carboxyl group. Section 1. Meet the carbonyl group.
Think about the sheer dynamic tension packed into this one tiny structure. The carbonyl group is just a carbon-oxygen double bond, but because oxygen has a much higher electronegativity than carbon, it acts like a magnet, constantly hoarding those shared electrons. This creates a highly polarized dynamic. The carbon becomes electron deficient, essentially acting as an electrophilic or Lewis acid center. The oxygen, on the flip side, becomes electron-rich, a nucleophilic or Lewis base center. This fundamental built-in polarity dictates exactly how these molecules are going to behave when they run into other chemicals.
And that single carbonyl group actually branches out into 2 completely distinct families based on what else is attached to the carbon. If the carbonyl group is bonded to a carbon and at least one hydrogen atom, boom, you have an aldehyde. But if that carbonyl carbon is sandwiched strictly between 2 other carbon atoms, it's a ketone. It seems like a minor tweak, right? But this seemingly simple difference in bonding drastically changes their chemical identity, especially when it comes to how easily they can be oxidized, which we'll see in just a bit.
Section 2. Naming rules and nomenclature.
Historically, chemists relied heavily on common names based on where the compound was discovered. Think vanillin from vanilla beans or acetone. But the IUPAC system gives us a foolproof, universal map. It comes down to 3 logical steps. First up, find the longest continuous carbon chain that contains the carbonyl group. Second, simply replace the standard alkane ending E with al if it's an aldehyde or wone if it's a ketone. Third, number the chain to give the carbonyl carbon the lowest possible number. And a quick pro tip, for aldehydes, that carbonyl carbon is always sitting at position number 1.
Section 3. Physical properties and behavior.
This perfectly illustrates exactly why structure matters so much. If you compare a handful of compounds with nearly identical molecular masses, say right around 58 to 60, you'll see vastly different boiling points. Take N-butane. It's completely nonpolar and boils at a chilly 273 Kelvin. But propanol, which is an aldehyde, and acetone, a ketone, suddenly jump up to 322 and 329 Kelvin. Why the huge leap? It's all because of that polar carbonyl group we just talked about. It creates weak molecular associations through dipole-dipole interactions. However, they still boil at lower temperatures than alcohols, like propan-1-ol, simply because aldehydes and ketones can't form intermolecular hydrogen bonds with themselves.
Now, when it comes to solubility in water, it helps to think of hydrogen bonding like molecular Velcro. The oxygen in the carbonyl group can easily form hydrogen bonds with water molecules. This makes the smaller, lower members of the family, like methanol and propanone, completely miscible. They just dissolve instantly. But as that carbon chain gets longer and bulkier, it acts as a massive hydrophobic barrier, effectively ripping that Velcro apart. So as the alkyl chain lengthens, solubility rapidly drops off.
Section 4. Key preparation methods. Let's look at how we actually make these things, starting with the Rosamond reduction. We kick things off with an acyl chloride, otherwise known as an acid chloride, and the goal is to swap that chlorine out for a hydrogen. The absolute key here is the catalyst. We hydrogenate it over palladium that's supported on barium sulfate. This specific catalyst is the secret sauce. It successfully stops the reduction right at the aldehyde stage, completely preventing it from overshooting and going all the way down to a primary alcohol.
Next is the Atard reaction, which is a brilliant method for preparing aromatic aldehydes. We start with toluene, which is just a benzene ring with a methyl group attached. If we used a standard strong oxidizer, it would blast right past the aldehyde stage and turn it into an acid. But chromyl chloride is perfect for this. It oxidizes the methyl group into an intermediate chromium complex, elegantly hitting the brakes on the oxidation process. From there, a simple hydrolysis of that complex yields our final target, benzaldehyde.
Section 5. Crucial chemical reactions.
So I want to pose a direct question to you.
Why is the nucleophilic addition mechanism so incredibly fundamental to both aldehydes and ketones? Well, think back to our very first principle, that highly polarized C-double-O bond. Let's see how that tension translates into an actual chemical reaction.
Because the carbonyl carbon is electron deficient, a nucleophile, which is our electron-rich attacker, swoops in and attacks it from a direction roughly perpendicular to the molecule's flat plane. The moment this new atomic connection forms, the carbon-oxygen double bond snaps open. It's fascinating to watch mechanically because the carbon's hybridization shifts dramatically from a flat sp2 geometry right into a 3D sp3 geometry. This produces a tetrahedral alkoxide intermediate. Finally, this intermediate snags a proton from the surrounding medium to form our stable neutral addition product. It's just a beautifully logical sequence of events.
Remember earlier when I mentioned that the structural difference between aldehydes and ketones dictates how easily they're oxidized? Well, here is the proof. Aldehydes are notoriously easy to oxidize into carboxylic acids. Even mild oxidizers can get the job done. Tollen's reagent and Felling's test are classic laboratory methods used to tell them apart. With Tollen's, oxidizing an aldehyde will actually coat the inside of your glass flask in a stunning, highly characteristic silver mirror. Meanwhile, Felling's test uses an alkaline copper sulfate solution. Heat an aldehyde with it and you'll get a very distinct reddish-brown precipitate. Ketones, they generally won't react to these mild tests at all.
Another absolute powerhouse reaction is the aldol condensation. The strict prerequisite here is that your molecule must have at least one alpha hydrogen. That's a hydrogen attached to the carbon sitting directly next to the carbonyl group. Because the carbonyl group pulls electrons away, that specific alpha hydrogen is uniquely acidic. When you react it with a dilute alkali catalyst, you form a beta-hydroxyaldehyde, literally called an aldol because it combines an aldehyde and an alcohol group. Then, this aldol readily loses water to create a stable alpha-beta unsaturated carbonyl compound. But what if an aldehyde lacks an alpha hydrogen entirely, like formaldehyde? Well, it can't do this. Instead, it undergoes the Cannizzaro reaction, where it self-oxidizes and reduces to yield an alcohol and a carboxylic acid salt.
In our final module, Section 6, the carboxyl group.
If you take the carbonyl group we've been obsessing over today and attach it directly to a hydroxyl group, you get the carboxyl group, the defining feature of carboxylic acids. A crucial thing to remember about these acids is that their acidity is heavily influenced by their substituents. For example, electron withdrawing groups pull electron density away, which stabilizes the conjugate base and makes the acid significantly stronger. These compounds are incredibly important. The higher members, known as fatty acids, occur naturally in fats, and even more critically, carboxylic acids serve as the essential starting material for synthesizing a massive array of other vital organic compounds, including anhydrides, esters, and amides. Which wraps up today's explainer. We've seen how a single, simple difference in electronegativity creates a polar bond that entirely dictates how these molecules behave, interact, and build upon one another. So I'll leave you with this final thought. How will you use your new foundational knowledge of the carbon-oxygen double bond to synthesize tomorrow's essential materials? Keep exploring, keep questioning, and I'll catch you in the next explainer.